Hello everyone. Before we dive into formulas, let me ask you a question. Have you ever wondered how we can be absolutely sure that a physics equation is correct even before testing it in the lab? The secret lies in dimensional equations. Dimensional equations are more than just a collection of letters. They allow us to convert units from one system to another, verify whether an equation is valid, and even derive useful relations between physical quantities. And the golden key behind this is the principle of homogeneity, which says that the dimensions on both sides of any physical equation must be the same. Once you understand this, you see how physics maintains its consistency across every measurement system.
Let's begin with the first use, converting units. Suppose we measure the same physical quantity in two different systems of units. Their numerical values may differ, but the product of value and unit always remains constant. In general, we write P equals n sub 1 into u sub 1 equals n sub 2 into u sub 2. If the quantity has a dimensional formula m to the power a, l to the power b, and t to the power c, the conversion factor uses the ratios of fundamental units of mass, length, and time in each system. The formula becomes n sub 2 equals n sub 1 multiplied by open bracket m sub 1 over m sub 2 close bracket to the power a multiplied by open bracket l sub 1 over l sub 2 close bracket to the power b multiplied by open bracket t 1 over t2 close bracket to the power c. This means we don't need to memorize endless conversion factors. Dimensional equations handle it for us. Let's test this idea with an example. We'll convert 1 Newton into dynes. Force has the dimensional formula mLT to the power minus 2. In the MKS system, 1 Newton equals 1 kilogram into 1 meter per second squared. In the CGS system, the units are grams, centimeters, and seconds. Substituting, we get N2 equals 1 multiplied by open bracket kilogram over gram, close bracket, multiplied by open bracket meter over centimeter, close bracket, multiplied by open bracket second over second close bracket to the power minus 2. This simplifies to 10 to the power 3 multiplied by 10 to the power 2 equals 10 to the power 5. So 1 Newton equals 10 to the power 5 dynes. This is how dimensional analysis quickly converts units across systems. Now, the second powerful use, checking if an equation is correct. Take the well-known equation 1/2 mv squared equals mgh. On the left side, 1/2 is just a pure number. So dimensions come from mv squared, that is, mass m multiplied by velocity squared. Velocity has dimensions lt to the power minus 1. Squaring gives l squared t to the power minus 2. So the left side is ml squared t to the power minus 2. On the right side we have mgh. Mass is m. Acceleration due to gravity is lt to the power minus 2. Height is l. Multiplying gives ml squared t to the power minus 2. Since both sides match, the equation is dimensionally correct. Without solving a single experiment, we just verified the equation. Let's move on to the third use, deriving relations. Suppose a physical quantity depends on several factors. We assume a relation of the form q proportional to x to the power a, y to the power b, and z to the power c. Then we substitute their dimensional formulas and compare powers of m, l, and t. This process cannot tell us the numerical constant, but it reveals exactly how one variable depends on others. For example, whether a pendulum's time depends on its length or its mass. Let's actually try this. Consider the time period of a simple pendulum. It may depend on the mass of the bob m, the length of the thread l, and gravity g. We assume t proportional to m to the power a, l to the power b, and g to the power c. Now substitute dimensions. Left side t has dimensions t. Right side becomes m to the power a, l to the power b, and lt to the power minus 2 raised to the power c. That is m to the power a, l to the power b plus c, and t to the power minus 2c. For both sides to match, the power of m must be 0, so A equals 0. The power of L must be 0 plus 1, so B plus C equals 0 plus 1. And the power of T must be 1, so minus 2C equals 1. Solving, A equals 0, B equals 1/2, C equals minus 1/2. Hence, T equals K multiplied by the square root of L over G. As you can see in the diagram of a pendulum, the bob swings back and forth, and the time it takes depends only on the length of the string and gravity, not the mass of the bob. This is a beautiful confirmation of real experiments. Let's quickly recap what we've learned. Dimensional equations have three major uses. First, they help us convert units, as we did with 1 Newton equals 10 to the power 5 dynes. Second, they let us check correctness of equations, like verifying 1/2 mv squared equals mgh. And third, they allow us to derive relations, like finding t equals 2 pi square root of L over G for the pendulum. Dimensional equations act like a bridge between mathematics and physical reality. I hope you now see how this tool saves us time, avoids mistakes, and gives deep insight into physics. See you in the next session with another fascinating concept.